Okay, class, chapter 1 of book 1. So we're going to be learning about our, eventually getting into derivatives, but we have to do quite a bit of work to set the stage for that. And so we're starting in the beginning of chapter 1 with secant lines and tangent lines. So secant lines you actually know a good bit about, even though you maybe didn't call them secant lines. And so we're going to start there. And we're going to set the stage by talking about a story where imagine that all of us in class got together and we are going to take a road trip together in a giant bus. And so there's a big class, so all 80 of us climbed into this like really stretched out bus. And we're going to start thinking about a particular story. We're going to start distance traveled is in miles, because we're all pretty familiar with traveling in a vehicle. And then we're going to talk about time in hours. And so when we do those conversions, those are miles per hour, something again, speed that we're very familiar with. And let's imagine that in this bus, we're driving along and we leave. Let's suppose we do this scenario where we're going to go from time 0, where we're going to leave Charleston, and then all the way over here on the x-axis, we're going to end up 4 hours later in Raleigh. This is a trip I personally happen to make often because I did all my graduate work in Raleigh and then I moved down here to Charleston for the job at the College of Charleston. And I made that trip often, go back during the move, and then also my mentor lived there, so I would do some research with him. And so it was, for me, pretty impossible to make that trip in under 4 hours unless I wanted to get a speeding ticket, of which that happened once. So, and maybe about midway along the way in that trip is a place called south of the border. And it's a weird little rest stop area at the border between North Carolina and South Carolina. And that's usually, let's just say it could be roughly around the 2-hour mark. Right, and again, we're going to imagine that we started from Charleston and we were just kind of leisurely leaving, and then we just started to accelerate. Maybe we were listening to some loud techno music or something and started to accelerate. And let's suppose this is the function y is a function of x. I don't have an explicit formula for it yet, but eventually we might. You know, it just gives the shape of the curve, and we can imagine what happens. And so I want to ask a few questions. And from Charleston to Raleigh, that distance, just to make it even, was about 280 miles. And south of the border, this is not to scale here, but it's about 120 miles to south of the border. So at this point here, this is the point, x is 2, y is 120 miles. And this is the point when we've gone 4 hours, we've traveled 280 miles. And then of course, 0, 0 here at the origin. And we want to ask some questions about our speed when we've traveled, let's say, over the first 2 hours of the trip. So it might be a good idea to pause the video now and see if you can answer this question. Just think on your own for a moment. If we went from Charleston to south of the border, that took us 2 hours. We traveled 120 miles. What was our speed during the first 2 hours of the trip? So you can pause the video and just think about that for a moment. What was our speed during that first 2 hours of the trip? All right, so then you come back and hopefully you all got to the place where you're able to say we did 120 miles in 2 hours, so 120 divided by 2 ended up being 60 miles per hour because the units are miles divided by hours in that case. And how about over the whole 4 hours? How fast were we going over the whole 4 hours of that trip? On average, if it took us 4 hours to travel 280 miles, what was our average speed for the whole trip? And we can say then, that's 280 miles divided by 4 makes 70 miles per hour. And then maybe we wanted to say over the second half of the trip. Now this last 2 hours, how fast were we going? Again, pause the video. This one might take a little bit more computation. On the second half of the trip, how many miles did we cover? We went from 120 to 280. So that's 160 miles. And we did that in 2 hours. So we actually really started picking up the speed. The average speed over the last 2 hours of the trip was 80 miles per hour. Well, how are we computing those? Let's think how I did that. Especially the last one, over the second 2 hours of the trip, really reveals something that helps us figure this out. We did, so the average speed from time x equals 2 to time x equals 4, we did this calculation. 280 minus 120 miles over 4 minus 2 hours equals 160 divided by 2, which is 80 miles per hour. And so notice what we've done there is we've taken 2 y values and subtracted them, divided by 2 x values and subtracted them. And so really, that should remind you of the slope that we did in the previous section, right? We were getting slopes of lines then. Change in y over change in x. y2 minus y1 over x2 minus x1. Delta y over delta x. So really this turns out to be a slope, right, of which line? The line between these 2 points. And that line has a slope of 80. So you know how to get equations of lines. Again, we reviewed that before. You know how to get slopes of lines. Again, we're reviewing from the previous section. The only part that's new is that we're now going to call this a secant line. So we just talked about lines in general, and now we have this adjective that goes in front of it. This is a secant line because it touches our function in 2 points. It's a line between 2 points on the curve, here and here. That's different than the secant line between these 2 points. So the first 2 hours of the trip, we said this line had a slope of 60. And you would have gotten the calculation the exact same way. Change in y, and this was the point 0, 0. So 120 minus 0, 2 minus 0, change in y over change in x, slope of 60. What makes it a secant line is that it touches your function. And maybe put the function in black, and we'll make it a little bit darker. This is our function f of x. So we can draw secant lines all over the place, right? Between any 2 points on the curve, and then we could go ahead and get the slopes of those secant lines. The key thing for us, though, is that the slopes of those secant lines represent something, in this situation, a miles per hour speed. And in general, a secant line, let's see, maybe we'll put it here. The slope of a secant line gives an average rate of change of y with respect to x. Which another way of saying that is it's an average rate of change over your y units divided by your x units, right? We did, this one was 80 miles divided by hours. So you take your y units, put that in the numerator, divided by your x units. In this case, we're all pretty familiar with that miles per hour is the speed. So it turns out for us, this is an average speed in this scenario. But depending on what your units were for y and your x, you just use those. So if it was like, let's say we had something like this, I'll put a little one over here on the side. Another example, just to give you a scenario, suppose we had a graph that represented the number of Facebook users over time. And this is time in years maybe since Facebook has started. And let's say they had a lot in the beginning, then maybe they were slow, and then they're kind of shooting up exponentially. So in this case, if you were to get a secant line between, let's say this is year 4 and this is year 10, the secant line in this scenario would then represent the average rate of change of the number of Facebook users over the years, right? Over, in this case, 6 years. Be the average rate of change of how many users we had. So you can always do this average rate of change over whatever your y units divided by your x units. Okay, again, in our scenario, this was average speed. Okay. But what we're really interested in, and that's good, that's all stuff that actually might be review for many of you. The part that we really want to do now, what we're going to lead up to in the first 1 to 2 chapters, is figuring out this question. Rather than getting an average rate of change, an average speed for this story, we're really interested in the fact that, and this often happened, that police sat at south of the border right there. They had a radar gun pointed at you. And so we wanted to know, what is the, not an average rate of change, not the average speed. We want to know what is your precise instantaneous speed, your radar gun speed, when the police is sitting at south of the border, exactly at time 2, how fast are you going? And so we want to get something called a tangent line. So I'm going to put that in there. Hopefully this red will show up. We want to know right here at this point, which is often called the point of tangency. And we're going to get really used to this word tangent. We want to get this, the slope of this red line. We'll put the red line in there, and this is a tangent line. So many of you have seen secant lines, you just didn't know they were called secant lines. But tangent lines probably new for most of us. And now we're going to spend a good bit of time talking about what is a tangent line. Okay, so we'll do that. I'll do that in the next video. So make a short one just about secant lines. Let's review a few things before we move on. A secant line does what? It touches your function in 2 places. It connects 2 points on your function f of x. When you get the slope of that line, you just do it as you normally do, change in y over change in x. And the slope of that line represents an average rate of change over some duration, right? It's always, in this case, this one here was from x equals 2 to x equals 4, a duration. This secant line here was from x equals 0 to x equals 2 over a 2-hour span. There's a secant line from here to here, that would be over a 4-hour duration, right? And then you're getting your y units divided by your x units. In the next video, we're going to talk about this red line and how do we get the slope of that red line.